Red drum, also known as redfish or channel bass, have experienced a recent surge of popularity that has resulted in a market shortage and higher prices, prompting investors to seriously consider raising these fish in captivity. Traditionally, red drum were commercially fished as 2 to 3-year-old juveniles in shallow bays and estuaries. These 3 to 8 pound fish were captured from small boats using gill nets and trot lines. Total landings from the Gulf and southeastern Atlantic states amounted to only 4 million pounds per year. Demand for this species dramatically increased during the early 80s, due in large part to the nationwide introduction of blackened redfish by Chef Paul Prudhomme of New Orleans. As demand increased, purse seiners began to target large offshore schools of adult red drum, typically 30 pounds or more. Between 1984 and 1985, landings increased from 3 million to 12 million pounds. This dramatic increase in production, composed largely of breeding-sized fish, alarmed fisheries managers and conservationists. Concerned that the reproducing populations of red drum would be diminished below maximum sustainable levels, the Secretary of Commerce closed purse seining for this species in 1986. As a result of this closure in offshore federal waters and closures in some inshore state waters, supplies of red drum have fallen far below demand, and prices have climbed from traditional levels of less than $1 per pound to as much as $3 per pound for whole fish. This has encouraged aquaculturists to attempt raising red drum on a commercial basis for the first time. The red drum is naturally a marine and brackish water species, but has been successfully grown in certain fresh waters and thus can be considered a candidate for freshwater as well as brackish water culture. Although commercial aquaculture of red drum has just begun, considerable information exists about fingerling production of this species because of extensive efforts to restock depleted populations of red drum in natural waters. For example, ongoing efforts by the Gulf Coast Conservation Association, Central Power and Light Company, and the Texas Parks and Wildlife Department result in the mass production and release of about 10 million 1-inch red drum fingerlings into Texas bays each year. The problem is that little information is available concerning culture of red drum from fingerling to market size. Potential red drum farmers hope to utilize much of the grow-out technology that has been successful in the thriving catfish farming industry. For that industry, 1979 production of only 40 million pounds raised in 30,000 acres has increased rapidly to current production of over 200 million pounds grown in 130,000 acres of ponds. Current farm gate value is approaching $400 million and significantly impacts the economy of the Mid-South. The first step in the process of raising red drum is collection of brood fish for spawning. This process may require a collecting permit, depending upon the state in which you are operating. Contact your county extension agent or local fisheries biologist to determine the appropriate state and federal permits required for the various aspects of red drum aquaculture. The process of collecting 20 to 40 pound red drum for use as broodstock can be time-consuming. The best results have usually been attained by fishing during their fall spawning season near passes connecting bays to the ocean. They've been captured with a variety of gear types, including gill net, trot line, purse seine, and beach seine. However, hook and line capture generally causes the least stress, particularly if the fish are caught by the lip. To improve the chances of hooking the fish in the lip, a 3 to 7/0 circle tuna hook is recommended. If the fish are not highly stressed during capture and transport to the hatchery, this is a good time to determine their sex and degree of egg maturation before placing them in spawning tanks. The sex of adult fish can be determined by examining the openings near the vent. Males have a single urogenital papilla posterior to the anus. Females have separate urinary and genital orifices. The genital aperture is located among flaps of tissue between the urinary duct and the anus. During the fall spawning season, it's relatively easy to determine if fish are completely mature by putting a little pressure on the lower abdomen near the vent and observing whether eggs or milk flow freely. However, if females are not fully mature, their stage of maturation can be determined by inserting a small glass tube called a catheter into the oviduct, removing a small amount of ovarian material, and examining it under the microscope. Fully developed eggs will be greater than 0.5 millimeter in diameter and pale yellow in color. In the hatchery, it is possible to induce mature red drum to spawn through hormone injection, but this procedure is rarely used because it tends to excessively stress the valuable broodstock. It is much more productive to vary the temperature and photoperiod, thereby allowing multiple spawns of brood fish over an extended period. The idea is to manipulate the length of day, as well as the water temperature, to simulate the passage of seasons. Redfish spawn during the manipulated fall season. The length of the day is usually controlled with lights activated by automatic timers. Water temperature is regulated either directly by submerged heat exchangers or indirectly by controlling the ambient temperature with air conditioning and heating units. To avoid toxic effects of excretory waste in the broodfish tank, it is necessary to continually exchange water at a rate of at least 100% a day. If outdoor water were used, the expense of continually adjusting its temperature for only one pass through the system would be prohibitive. Consequently, most hatcheries have installed water reuse systems in which wastewater is treated and returned to the tank with little change in temperature. Reuse systems employ biological, mechanical, and germicidal treatments. Biological treatment relies on bacteria to convert toxic ammonia and nitrite to non-toxic nitrate. Both unionized ammonia and nitrite are toxic to fish at concentrations above 1/2 part per million. Biological treatment is a natural process which can be accelerated by providing a large surface for attachment of bacteria and a continual flow of oxygenated water past that surface. These features have been incorporated into many different designs, all of which are effective. The rotating biodisc filter, for example, utilizes closely spaced fiberglass plates as a surface for attachment of bacteria. The rotating action provides continual exposure to both wastewater and air. A variation in design utilizes air conditioning filters as a surface for bacteria. Supplemental aeration between the plates assures that the bacteria receive sufficient oxygen to detoxify the water. In a third type of biofilter, hollow plastic balls provide the surface for bacteria. Oxygen is incorporated as the spray drips over the plastic balls. Biological filters tend to reduce the pH of the recycled water over time, so it's necessary to include oyster shell or a similar source of calcium carbonate in the treatment system to maintain pH within the range of 7.8 to 8.2. Mechanical treatment of wastewater involves the removal of suspended solids. This is most easily accomplished with an ordinary swimming pool filter. Particles trapped on the surface of the sand are flushed out by periodically backwashing the filter. The final step in the treatment process is control of parasites and other microorganisms which might infect the broodstock while they're in the conditioning process. Ultraviolet light has been commonly used. However, ozone and photozone have also been effective. After these treatments, water is returned to the broodstock tank. A small laboratory is essential for maintenance of water quality. Basic instrumentation includes a refractometer used to measure salinity. The preferred salinity for spawning and hatching of red drum is 28 to 35 parts per thousand. An oxygen meter to determine both oxygen and temperature. Dissolved oxygen should be maintained above 5 parts per million. A spectrophotometer to accurately measure ammonia and nitrite concentrations. Both of these waste products are extremely toxic to fish, above 1/2 part per million. And a pH meter. It's important to monitor the acidifying effect of the biofilter. Typically, red drum are introduced into the temperature photoperiod conditioning cycle during the winter phase. They're fed a variety of cut fish, shrimp, and squid. Small food fish have their air bladders cut so that they'll sink to the bottom and not get caught in the egg skimmer or drain system. Typically, red drum are ferocious feeders while in the conditioning process. The natural annual cycle can be compressed to 150 days under controlled laboratory conditions. Initially, temperature is lowered to 15 degrees centigrade and day length is reduced to 9 hours. For 25 days, both temperature and day length are gradually increased to a high of 30 degrees centigrade and 15 hours to simulate the passage of spring and summer. During the next 50 days, temperature is reduced to 24 degrees centigrade and day length reduced to 12 hours to arrive at the simulated fall spawning season. Several days prior to spawning, male red drum darken in color above the lateral line and begin drumming and courting the females. Females often show red, swollen vents. Spawning usually occurs within 3 hours after the lights are turned off. Females typically spawn several 100,000 eggs, which are fertilized by milt from one or more accompanying males. Fertilized eggs are collected the following morning. Newly spawned red drum eggs are clear, spherical, and approximately 1 millimeter in diameter. Their large golden oil droplet makes them buoyant and easy to collect by simply skimming the surface water of the maturation tank. The eggs are concentrated in an adjacent smaller tank lined with a fine mesh bag. In the morning following a spawn, the eggs have been water hardened and can be handled with a soft net. A convenient way to estimate the number of eggs in a spawn is to pour them into a graduated cylinder and allow them to float to the top. The volume that they occupy is then multiplied by 1,000. In other words, 1 milliliter contains roughly 1,000 eggs. Following enumeration, eggs are placed in an incubator tank with moderate aeration to keep the eggs stirred. Eggs hatch about 24 hours after fertilization. These are developing embryos. 35 to 40 hours after hatching, the larvae absorb their yolk sacs and develop mouth parts. At this time, they must be harvested from the incubator tank and fed. This is a simple but effective larva harvesting box. Water from the incubator is drained into the box where the larval fish are concentrated. Excess water flows out of the box through the screen on the standpipe. A stream of bubbles from an air hose collar helps prevent the larvae from impinging on the overflow screen. A sample of the concentrated larvae is collected in order to estimate the total population. Fish of this size can be placed in water within an oxygenated bag and shipped for periods of up to 24 hours in tropical fish shipping boxes. During shipping, oxygen will diffuse into the water, maintaining a concentration sufficient to keep the larvae healthy. The next objective is to raise the microscopic larvae to inch-long fingerlings. There are basically two approaches to this phase of the red drum production. One technique utilizes fertilized outdoor ponds, while the other involves rearing larvae at high density in indoor tanks. The outdoor pond technique provides food to the larvae by stimulating high densities of small zooplankton through fertilization. Outdoor fingerling ponds are usually 1 to 2 acres in size, approximately 3 feet deep, and sloped to drain into a harvest basin at one end. The pond is filled with seawater of at least 20 parts per thousand salinity, which is passed through a 0.5 millimeter filter to eliminate predators, such as fish and crabs. The seawater is then fertilized with a combination of inorganic and organic fertilizers. The inorganic fertilizer first stimulates a phytoplankton bloom. These microscopic plants give the pond its greenish or brown color and are the food for larger zooplankton on which larval fish feed. Subsequent additions of organic fertilizers stimulate the growth of zooplankton. A variety of fertilization regimes have been used to rear red drum. This is an example of one that has been successful at the Perry Bass Marine Fisheries Research Station in Palacios, Texas. As can be seen from this schedule, it's important to maintain the plankton bloom throughout the growth cycle by regular application of various fertilizers. Density and type of zooplankton should be monitored weekly throughout the grow-out cycle to assure an adequate food supply for the rapidly growing fish. Zooplankton are quantitatively sampled by pulling a net a given distance through each pond, or by pumping a measured volume of water through a filter which retains the plankton. The dominant zooplankton groups in a properly fertilized larval rearing pond are rotifers and copepods. Rotifers are one of the ideal foods for the first feeding red drum larvae because their small size is appropriate and they're slow swimmers. A density of 100 to 200 rotifers per liter of pond water has resulted in good growth and survival of red drum larvae. Copepods are the other dominant type of zooplankton found in fertilized outdoor ponds. Nauplii, the larvae of copepods, tend to dominate newly fertilized ponds and are of suitable size for first feeding by red drum larvae. However, adult copepods, which can reach lengths of several millimeters, are too large for first feeding larvae. It's important to coordinate stocking of the pond with peak abundance of rotifers and larval copepods. Consequently, it is necessary to fill and fertilize ponds about 10 to 14 days before larvae are ready to stock. Numerous other invertebrates such as larval barnacles, crabs, mollusks, polychaetes, and aquatic insects may be present at various times in sufficient number to provide a substantial portion of the larvae fish diet. After 30 to 40 days in the fertilized pond, fingerlings reach 1 to 2 inches in length and are ready to harvest for subsequent stocking into grow-out ponds. The pond is harvested by draining water through screens which prevent fish from escaping. The majority of the fish usually avoid the harvest basin until the pond is nearly empty. When the fingerlings enter the basin, they are collected with dip nets and placed in pre-weighed buckets of water. The difference between the original weight of the bucket of water and the new weight of the bucket with red drum is calculated. This weight is divided by the average individual weight of the fish to estimate the number of fingerlings harvested. Fingerlings are transferred to the grow-out area in hauling containers equipped with oxygenation or aeration mechanisms. Oxygen should be maintained at or near saturation and should never fall below 4 parts per million. Another method of raising red drum fingerlings involves high-density culture of larval fish under controlled conditions. Rather than relying on a natural zooplankton bloom in an outdoor pond, specific types of plankton are cultured indoors. This involves culture of phytoplankton to feed rotifers, rotifers as food for first feeding red drum, and brine shrimp to feed advanced red drum larvae. The unicellular microalgae, Tetraselmis or Isochrysis, have been the preferred species of phytoplankton for feeding rotifers. Each is relatively easy to grow and provides excellent nutrition of the proper size for rotifers. These can be purchased as pure cultures, which are sequentially transferred to larger volumes of sterile, nutrient-enriched seawater. This process culminates in the production of large quantities of microalgae. Rotifers are ideally suited to mass culture since under optimal conditions, concentrations of 150 to 200 rotifers per milliliter can be maintained for about a month in an algae-rich culture. In addition to algae, rotifers can also be grown on yeast and fish oil. This procedure reduces the time and labor involved in raising phytoplankton. Rotifers are harvested from the mass culture tank by draining a volume of the culture water through a 48-micron sieve. The rotifers are rinsed, counted, and introduced to the red drum larval tank at a density of 3 to 5 per milliliter. 9 to 11 days after hatching, red drum larvae begin the transition to a larger food. Brine shrimp are a convenient food at this stage. They can be purchased as dried, inactive cysts, which are easily hatched in 24 hours by aerating them in seawater. They are harvested, counted, and fed to the red drum fry in a manner similar to the feeding of rotifers. 10-day-old red drum fry are voracious feeders which consume a tremendous number of brine shrimp. A density of 1 to 2 brine shrimp per milliliter is maintained until the fish larvae are 15 to 20 days old, at which time they can be weaned to a less expensive prepared diet. The most common method of growing red drum fingerlings to market size involves the use of outdoor ponds. The location chosen for grow-out ponds will have a great bearing on the potential success of the farm. In selecting a site, one should consider not only water and land, but infrastructure characteristics as well. Water quality and quantity are of primary importance. Red drum are known to be susceptible to low winter temperatures, particularly if temperature drops abruptly. They prefer temperatures between 24 and 30 degrees centigrade, and if exposed to rapid or prolonged exposure to temperatures below 10 degrees centigrade, become severely stressed and may die. For example, large-scale kills of wild red drum have been documented in shallow bays during unusually severe cold fronts. Low water temperature is undoubtedly the biggest risk factor associated with red drum grow-out. Management approaches to deal with the potential for winter mortality include stocking advanced fingerlings in the spring and harvesting marketable fish prior to winter, or overwintering the fish in waters kept warm by increased pond depth, geothermal heat, or a greenhouse cover. Red drum can tolerate a wide range of salinity. They've been collected in natural waters ranging from nearly fresh to saltier than seawater. Preliminary data suggest that red drum raised in fresh water are less tolerant of cold temperatures than those raised in seawater. The least stressful salinity is thought to be near the middle of this range, about 10 to 30 parts per thousand. In some cases, red drum have grown remarkably well in fresh water. However, these situations generally involved power plant reservoirs with heated water, high levels of chlorides, and adequate calcium hardness. There is still much to be learned about commercial production of red drum in fresh water, but preliminary recommendations are to avoid fresh water when chloride levels are less than 150 parts per million, when calcium hardness is less than 100 parts per million, or when temperatures fall below 15 degrees centigrade. Do not underestimate the quantity of water needed for a pond grow-out system. A conservative rule of thumb is to provide a pumping capacity of 50 gallons per minute per surface acre of ponds. This could represent a major cost if water must be pumped from a considerable depth. It is important to select land which is suitable for pond construction. Desirable characteristics include soil with at least 25% clay to prevent seepage, elevation of at least 5 feet above sea level, and a water table at least 3 feet deep to allow for pond drainage and to reduce construction cost. And finally, topography that is nearly flat to reduce earth-moving cost. A final series of considerations in selecting a grow-out site is the available infrastructure. For example, one should determine the property's access to electricity, roads, feed mills, and processing plants. Pond design in general follows that which has proven successful for other warm water species, such as catfish. Ponds should be about 3.5 to 5.5 feet deep, with sloped bottoms to allow complete drainage. Size and layout of the ponds will vary depending on the type of culture to be practiced, that is, extensive, semi-intensive, or intensive. Extensive systems involve use of large, natural water bodies, which are not easily manipulated by typical management procedures. For example, extensive culture techniques are being used by brackish water impoundment owners in Louisiana. Semi-intensive systems utilize drainable ponds of 5 to 20 acres, which are designed to facilitate water exchange, feeding, and aeration. One semi-intensive design uses 2.5-acre ponds for production of 1-year-old fish and 10-acre ponds for the production of 2-year-old fish to more efficiently utilize land. This design also allows for a more accurate assessment of survival as the fish are transferred between ponds. Regardless of the grow-out system employed, water quality must be maintained in the ponds for the fish to survive and grow. Dissolved oxygen levels fluctuate over a 24-hour period, from a maximum in late afternoon to a minimum just before sunrise. If early morning readings are less than 4 parts per million, supplemental aeration and/or water exchange should be employed to increase dissolved oxygen. If values consistently fall below 3.5 parts per million, feeding should be reduced or discontinued until conditions improve. A water exchange of 5 to 10% a day is suggested during the warmest part of the growing season, May through October. Aeration can be achieved by injecting air into the water or by spraying water into the air. A high-quality feed with roughly 40% protein is required for good growth. Pellet size is increased as fish grow larger. Feeding rates are determined by estimating survival and growth rate at least once a month. Distribution of feed in large ponds is often accomplished with mechanical blowers, just as it is in the catfish farming industry. Intensive systems are high-density culture units, which can be placed indoors to avoid problems with low winter temperature. At this indoor grow-out system near Rockport, Texas, fish are grown in fiberglass troughs or raceways that measure 45 feet long by 8 feet wide by 3 feet deep. These raceways have produced yields of up to 2,000 pounds of fish. Biofilters are used to detoxify waste and minimize replacement water requirements. Water movement is accomplished using airlift pipes, in which water is drawn into the base of the pipe by the action of air being injected at a higher point. The water that is lifted with the air is discharged at the top of the pipe through elbows, which are oriented to create a single large circulation pattern within the tank. Backup systems for maintaining sufficient dissolved oxygen in the event of an equipment malfunction or a power failure are mandatory in high-density recirculating systems. Cylinders of compressed oxygen provide a temporary backup that is not dependent on electrical power. In an intensive culture operation, the fish derive all of their nutrition from a prepared diet. Thus, feed composition and the feeding regime are critical. Red drum fry are typically reared to juvenile size on trout or salmon feed containing 48% protein. Then they can be grown to harvestable size on a 40% protein diet. The food conversion ratio for a commercial intensive culture operation can be as low as 1.2 to 1. Feed can be distributed by hand with a continuous feeder or by using a demand feeder in which the fish activate the distribution mechanism themselves. Regardless of the distribution system used, it is important to offer feed in small amounts several times a day so that fish will eagerly consume it as it hits the water. This lessens the quantity of uneaten decomposing feed, improves water quality, and reduces the load on the biofilter. It's also important to routinely observe the feeding behavior of the fish and reduce or temporarily discontinue feeding if they lose their appetite. Although there are literally dozens of diseases and parasites which can affect red drum, one of the most common is the parasite Amylidinium ocellatum. Since this parasite attaches to the gills and interferes with respiration, heavily infected fish tend to congregate near the pond surface, aerators, or water inflow pipes in an attempt to obtain more oxygen from the water. Infected fish may also appear to cough water while trying to flush the parasite from their gills. While fish behavior is easily observed in raceway systems, their behavior is less obvious in turbid grow-out ponds. Therefore, it's a good practice to occasionally sacrifice a fish and check its gills for amylidinium infestation. Although the parasite has been successfully controlled using chelated copper at 4 to 6 milligrams per liter for 24 hours, maintaining good water quality through careful pond management is much more cost-effective. Harvesting and processing of red drum will probably utilize much of the same technology as is used by catfish farmers. Fish are concentrated by tractor-pulled seine and then transferred to live haul trucks with a hydraulic loader. Conventional fish processing equipment can be used to efficiently dehead, skin, and eviscerate fish. The fish can be filleted either mechanically or by hand. A variety of fresh and frozen market forms can be produced. In conclusion, there is a strong market-driven interest in aquaculture of red drum. This should continue to be the situation so long as wild stocks remain suppressed. It's fortunate that much is known about the process of spawning this fish, hatching its eggs, and rearing the larvae to fingerling size. However, our experience with grow-out techniques for red drum is limited. Despite the uncertainties, several commercial hatcheries and grow-out farms are already operating in Gulf and South Atlantic states. A few thousand pounds of farm-raised red drum have been harvested, but the business is still too young to allow accurate estimates of profitability. Many entrepreneurs feel that the potential for farming saltwater species such as red drum is great, and that the size of this industry will soon rival the thriving catfish farming industry. As with any new business, one should weigh the commitments, the risks, and the potential profits carefully before making a decision about entering this field. If more detailed information is needed, contact your local county extension agent for assistance, or request a copy of the Manual on Red Drum Aquaculture, which is available from the Texas Agricultural Extension Service.